Okay, friends, let's talk about the DEM of Difference Lab. We're going to be looking at two different digital elevation models, or DEMs, that came from LiDAR data. And we had a repeat LiDAR survey. They were surveyed over the St. Vrain River in Lyons before and after the 2013 Front Range flood events. So you can download the data for this. It's in a geodatabase on DEM of Diff. It's a zip file on Canvas for this assignment. In that, we have those two digital elevation models, or DEMs, as well as a polygon file that you'll use to figure out how much elevation and volume change occurred within a particular area. So for the write-up, please include a brief introduction, kind of describing what happened, what we're doing, and why, where these data are from, as well as a brief description of the workflow. Please cite the LiDAR data, and you can find the XML files in that zip file as well. As well as document the crucial steps for the major parts of this assignment. Let's take a look at the DEM. I'm going to do a kind of brief overview of what we're doing here. Let's see here. First one is from 2011 on the St. Vrain. So this is the Front Range, Lyons is here, Boulders to the south. And I've just got a little bit of an area where this South St. Vrain Creek comes in. And you can see the polygon where that reaches. Got the 2013 DEM, and I've got it colored. And then I made a hill shade of the 2013 DEM as well. And so we'll just zoom in there and you can kind of see everything. I'll take the background maps off. I made that 2013 DEM transparent under appearance and the slider scale to show the colors and the hill shade underneath. So you can see this is where the river moved. I didn't make a hill shade of 2011, but you could do that and compare the two. The river moved quite a bit here. To do this, what I'm going to call DOD or DEM of difference, we have to do some things to make sure the two rasters are going to line up with each other perfectly. All the cells need to be on top of each other. They need to be the same size and the same projection. I downloaded these digital elevation models from the state LiDAR depository website, and they just come in whatever format they were collected in. And so in this case, we've got the 2011 one, which is in, let's take a look. Looks like it's in some kind of foot, NAD 83 Harn feet. And then let's take a look at our 2013 DEM. And that is in UTM. All right, so we'll use the 2013 one as our base, and we'll line up everything from the 2011 one. So make sure it equals the projection, cell size, alignment, etc. with the 2013 one. That'll be our base one. So the first thing we'll need to do is project the 2011 raster. And all these steps are outlined in detail in the walkthrough that I've included. So we'll put in our raster. We will give it a name. We could call it UTM. Output coordinate system. We'll just make sure that we're going to get the 2013 one. The resampling technique. This is a critical step here. I learned the hard way that You cannot use nearest neighbor for continuous data. That's only for categorical data. So you can use one of these other techniques. I'm just going to choose bilinear. This is an interpolation technique, which works for continuous data. You can choose the output cell size. Again, for 2013, we want to make sure that the same cell size exists between the two. And it shows you right here that we have 0.75 and 0.75, so and that's in meters. Now, the last thing we're going to do is we want to make sure that the cells overlap perfectly. We don't want them to be offset when we do this difference. So I'm going to click on environments and scroll down. And you can see right here, I can do snap raster. I'm going to choose 2013 there. Take a look at what snap raster means. Basically, it says it will adjust the extent of the raster so that they match the cell alignment. And if the cells are the same size, which they are, which we told it to be in the previous step, then everything will line up perfectly. So I've done the snap raster for the 2013 as my base. I've done the coordinate system from 2013 DEM, and I did bilinear interpolation. So I'll go ahead and run that. So now what that has done, and I did that already, this gives me a raster that's aligned. Now, because rasters can have meters in the coordinate system, like UTM, XY values, the Z values can be whatever the raster value wants to be, whatever that happens to be. And so take a look at the two raster values and make sure that they're in the same vertical units. If they're not, you can use Raster Calculator to convert them. Again, we want to convert everything to the 2013 unit system and coordinate system. All right, so I've done that, and now I've got a 2011 raster that's in the same coordinate system and same vertical units as the 2013. And to get my DEM of difference, all I have to do is use Raster Calculator again, and I'll take a difference between the two. So a DEM of difference, I'm taking the difference. I'll let you guys figure out which way you want to do it. There's basically one way to do it, and that way is so that if we have an increase in elevation from 2011 to 2013, we want to have positive values. And if we have a decrease in elevation, we want to have negative values. So I'll let you figure out which order of operations there. Now that we have created, we use Raster Calculator to create this digital, so this DEM of difference, we should get values that range between plus or minus like 20 meters. So just kind of for your reference. It'll be black and white when you create it. I've gone and created a classified color scheme here where red is negative and blue is positive. So if you bring up symbology for this raster, you can do classification. You can do stretched. It's a little harder to get it symmetrical, which is important. I included a screenshot showing this. I did 7 classes here. You could certainly do more if you wanted. I did an odd number so that we have 0 in the middle, which is white. And then we have, or no color. Actually, I think I did no color for that. Yeah. And then -1 meter is going to be this light red, +1 meter is going to be this light blue, and then I went all the way up to so -1, -2, -4, 1, 2, and 4. So it's symmetrical. That way, when you've got a light blue versus a light red, they're going to be in the same range. The DEM of difference goes beyond -4 and +4. I just chose those as kind of like the threshold for saturation or darkness in the color, again, to be symmetrical. I made that a little bit transparent so you can see it over the hillshade. And then now you can see, because we have the 2013 DEM as the hillshade, you can see where a new channel was cut. You can see where deposition occurred in these bars. There's a lot of incision. Here's the old channel that filled in. And this is the kind of illustration of the changes in elevation across this area. The next step that we'll do once we've done this DEM of difference is to estimate the change in volume within this polygon. And so what I've done is I traced the outline of the kind of the channel and the floodplain. We'll use this area, this polygon, to sample this raster using zonal statistics as a table. And that will give us some information that we can use to calculate the change in volume. So go to geoprocessing, zonal statistics as table. I'm going to use the zone data. So this is going to be that polygon. If I had more than one polygon, it would give me a different row in the table for each, say, object ID or something like that. In this case, there's only one. The value raster is going to be what we're sampling. I called that SVDOD. And then the table can be whatever, calculate all the statistics, go ahead and run that. So let's open that table up. And there was only one polygon, one object ID, and so we get one row. And you can use, there's different pieces of information you could use here. That I think the most straightforward one is to take the mean. So this is the average of all the cells in here, plus or minus, you know, the change in elevation. If you take the average of that, that's going to be the average change in elevation across the whole thing. And then you can use that information with the area, which is going to be in the units of this polygon, which is meters. So this is meters squared, to estimate the change in volume. So I ask you to estimate the change in volume, as well as in cubic meters, as well as the change in weight of sediment. So what's the mass of sediment that exported of this reach, using an assumption for the specific weight of the sediment of 2.65. And so that is the ratio of the sediment density to the density of water. That's what specific weight is. And you can use that then to estimate the mass in kilograms or metric tons. All right, so that's one thing we can do is estimate volume changes and mass changes. The other thing we can do is figure out the uncertainty and bias in this DOD. So I have asked you guys to create a polygon shape file and draw two of them over a flat area and a steep area. So these are areas where we would expect no change to occur. So they're outside of the floodplain. And so I've got a flat area over here and just an agricultural field. I've got a steep area over here. So the flood did not impact these areas, and so we wouldn't expect a change to occur. So I've created these two polygons, and we'll use zonal statistics as table again. In this case, it's called sample DOD. Let's take a look at the attribute table here. All right, you can have the object ID or ID, you could put something in here. We just want to make sure they're differentiated, so that you're going to get two different pieces of information, two different rows in the zonal stats tool. So that's the zone field was ID. You could use object ID or something else. That's fine too. The value raster is what we're going to be sampling. So that's the DOD that we created. We'll create a new table and calculate all the statistics. Go ahead and run that. And now we have two rows, so one for each polygon. We'll look at some different statistics here. We'll look at the mean and then the standard deviation. The mean is about negative 0.11 to 0.13 meters. So 11 to 13 centimeters, and it's negative. And so because it's negative, that means we have a negative bias, meaning that the DEM of difference is overall more negative than positive. So what we can do is correct that DEM of difference by either adding or subtracting. In this case, because it's negative, we want to add those values back to the DEM of difference, and basically we're going to raise it back up, hopefully so that on average it's 0. And then we'll also note the standard deviation. We'll look at that in a minute. So what we'll do is we'll take the average of these two values. So I'll just estimate that briefly as 0.12. I'm going to go back to my raster calculator. Take my SVDOD and I'm going to add 0.12, and we'll call this SVDOD corrected. All right, so now it's it doesn't have that color scheme. It's just black and white. Kind of looks like an X-ray. Now let's go ahead and run that zonal stats tool again and see what the mean is. Take my sample DOD as the polygon. I'll use my corrected DOD for the raster. And I'll go ahead and run that and see what happens. Now my mean is much lower, still there, you know, and in one case it's -1 centimeter on average. So that's a lot better. So we did a very quick and dirty sampling of the error here. We could have sampled a lot more areas, right, to get a better estimate. And then we adjusted the DEM. We basically shifted it up so that's closer to 0 on average. The standard deviation shouldn't change. The last thing we could do then is we could go back and estimate the volume again of change, because it was a bias to be negative. So go back and run your zonal stats using this polygon and see if the volume calculation that you made and weight calculation changed at all. It should obviously shift up a little bit. And what that calculation is telling you is how much sediment actually left this reach. We saw that some eroded and some deposited. It might be close to 0, I don't know, but we'll take a look at that. I can tell you that if you were to do that estimate up here in these reaches, everything would be negative. We had a lot of sediment leave the hill slopes and then come out and deposit in the Front Range in the Piedmont area. So last thing we'll do is use the standard deviation to estimate what we consider not statistically significant different changes. And what that means is if we are within certain number of standard deviations, we can assume that they're not statistically significantly different from the mean, or in this case, which would be 0. So what we'll do is take the average of these two standard deviation values, and then we'll use the raster calculator again to remove those values. Just take a look real quick at this, okay. All right, so what I'm going to do is I'm going to take my corrected DEM of difference, and I'm going to say if it is, oh yeah, the last thing I forgot to mention is that we'll take the average of the standard deviations, and we'll take 2 standard deviations to be the outer edges of which we'll say is significant. Any changes within 2 standard deviations we'll say is not significant. 2 standard deviations give us, if we assume a normal distribution, they give us about, I think it's 67% of the data should be within those. And so anything outside of that is going to be kind of more extreme, and this is kind of an arbitrary threshold, but one we'll use to say if you're within that 2 standard deviations, it's not a significant change, it's within the noise. But if it's greater than those 2 standard deviations, then we'll say it's a real change. All right, so I'm gonna really quickly calculate this. So 0.034 plus 0.073 divided by 2 times 2. So about 0.11 is going to be our 2 standard deviations. So 11 centimeters, if you're plus or minus 11 centimeters, then it's a real change. All right, so what we'll do is we'll say if this is greater than 0.11, and then we'll use the Boolean operator, or, so this vertical bar is or, and we'll say that if it's less than 0 or negative 0.11, and so what this should do is create a logical raster where everything is has a value of 1 if it fits these conditions, and it has a value of 0 if it doesn't. So let's just see how this goes. We'll call it a mask. All right, so we got to make sure that when we do these, we need to put the first argument in parentheses, so that it'll run that whole argument. So this is what you actually need to put in. So parentheses, we have the corrected DOD here. So we say greater than 0.11 and close parentheses. This is the vertical bar, which means or, and then less than negative 0.11 in parentheses. So if we run that, we get a logical raster with values of 0 and 1. So 0 is where everywhere where we're within that uncertainty error. So we're going to say that's 0, and then everything that's purple in this case has a change that's more real than that. You can see there's these weird stripes going on. So this isn't perfect, right? And this is from LiDAR data. These stripes are where I'm assuming where the LiDAR was a little bit off or a different angle or something like that. And so it's not, this DEM of difference is not super accurate everywhere. But where the channel's flat, you can see that there's significant differences within this area. So we'll call it pretty good within the channel area. How do we use this mask? Well, we can go back to Raster Calculator using that a lot. And we can put in that corrected DOD and then multiply it by our mask. And then we'll call it, the DOD, we'll call it masked. So everywhere that is, where the change in elevation was greater than that 2 times the standard deviation, will just be multiplied by 1. And all the cells that are outside of that will be multiplied by 0. So now we've masked it. We basically removed those values or set them to 0. And you can then use the same color scheme as before. So to do that, so I'm going to click on the stretch color bar. I'm going to click on these 3 lines here, import from layer. And then we'll go back to that SVDOD. It's already made that color scheme. And it just imports our color scheme. I'll take all these things off. And now we have a DOD that's been masked. So we've removed the values that we said were not significant within 2 standard deviations. We've adjusted the bias on it from our sampling scheme. And then we could finally, once again, run this volume calculation. Maybe we should wait to the end to run the volume calculation for the full kind of correction. This will be our best estimate of volume change. So those are all the major steps. Take a look at the walkthrough and make sure you respond to all the prompts that are in italics and bold. And now you know how to make a DEM of difference and estimate change in land over time. There's a quarry right here that's abandoned, and we could use the same technique to track the change in the volume of rock excavated from this quarry over time. You could also use this to, for example, look at an excavation or construction site and look at your kind of cut and fill over time and balance. So these are things you could do if you have the topographic data, either from LiDAR, from a land survey, or from photogrammetry, which we'll learn about a little bit later.